Good afternoon, everyone. Welcome to today's talk. Our speaker today is Paolo Serra. Paolo studies galaxy evolution primarily through observation of galaxies in the nearby universe, comparing them with simulations. Much of his observational work is based on observation of H1 gas with video telescopes, and he has worked with for several years with the ASKAP precursors and pathfinders, such as the APERTIF, ASKAP and MeerKAT. And it's the PI of one of MeerKAT's large projects, which is the MeerKAT Fornax Survey. So it's my pleasure to introduce Paolo Serra today to talk to us about the Ubiquitous H1 tails and clouds in the MeerKAT Fornax Survey. So over to you, Paolo.
Okay, can you hear me?
Yes, very loud and clear.
All right, very good. Thanks, Sam. Thank you for the invitation. It's a pleasure to give this talk on the MeerKAT Fornax Survey. Yeah, as you said, this is one of the large surveys on MeerKAT. In fact, possibly it's the smallest of the large surveys on MeerKAT. But nevertheless, it's a significant chunk of amount of MeerKAT data that is coming our way. And I'm quite excited to share with you some of the first results that we're getting. Before I start, I'd like to acknowledge the help of the full MeerKAT Fornax Survey team that you can see on this slide. And in particular, I'm highlighting the name of young students or postdocs that have been or still are based at the Observatory of Cagliari with me. This is an observatory which is part of the Italian National Institute for Astrophysics, INAF. And some names might be familiar to you as well. These are the people that really made this work possible, and throughout the talk I'll highlight their work, and in particular some of the papers that came out over the years while we were busy commissioning MeerKAT and taking commissioning data. Anyway, back to the main topic of the talk. This is a project where we're trying to study in exquisite details how galaxies evolve inside the very nearby galaxy cluster called Fornax. And as I hope I'll convince you, it's a target that is worthwhile studying and for which MeerKAT is really an excellent instrument. The broad goal of this project, the broad context, is our quest to understand why and through what processes the properties of galaxies depend on the properties of the environment within which they live. Now, the fact that the properties of galaxies are linked to the properties of their environment has been known for a very long time, essentially since the beginning of modern astronomy. Already observers such as Herschel and Hubble noticed that galaxies look different depending on how closely packed they are together. In denser regions of the universe where galaxies are quite close to one another, and in the most extreme cases, you can find thousands of them within a few cubic megaparsecs, galaxies tend to look like the one that you see here on the bottom left. This is an early type galaxy. It's got a smooth appearance, a very regular morphology, with very little structure within it. And it's characterized by a red color because it's dominated by old stars. And this means that it lacks a substantial population of young, massive blue stars because most likely it has very little cold gas from which to form stars. At the opposite end, at the opposite extreme, you have galaxies that live in very low density environments in the universe, and these ones look like the galaxy on the bottom right on this slide. So it's a spiral galaxy, obviously, a galaxy with a fairly complex morphology, lots of structure, clearly the well-known spiral arms, which are dotted with blue knots of young stars. That's where dense cold gas is located and where star formation takes place. And so when you look at the difference between these two objects, the one on the bottom left, an early type galaxy, the typical object in a high density environment, the one on the bottom right, a spiral galaxy, a typical object in low density environments, you immediately realize that this relation between galaxies and their galaxy morphology and their environment has a lot to do with the cold gas content of galaxies. The reservoir, the fuel for star formation, and therefore the material that determines the phase of galaxies, that determines their optical appearance. It is therefore probably no surprise that one of the key tracers to understand how galaxies change shape and morphology and appearance as they move from low density regions of the universe to high density regions of the universe is indeed neutral hydrogen gas, that we can observe through the 21 centimeter emission line in the radio regime. H1 is indeed the most massive component of the cold interstellar medium of galaxies, and so it's really the basic reservoir for star formation, and so one of the main factors in determining whether a galaxy is going to have an early type morphology, a regular, passively evolving with little star formation, or a spiral late type morphology with lots of gas star formation, spiral arms, and so on. And so indeed, H1 has been a key tracer over the past few decades to understand how galaxies transform from one morphology to another as a function of environment density. And so let me just walk you through some of the key steps that have been taken in this general context through H1 observation, starting from the work by Giovanelli and Haynes that you see in this slide. And so what they did in the 80s was to observe large numbers of galaxies with the Arecibo telescope. That's a single dish where you don't actually resolve galaxies spatially, but you can very quickly measure how much H1 they contain. And on this plot, you see the H1 deficiency on the vertical axis, plotted against the distance from the center of a particular cluster, Abel 2147 in this case, for a number of spiral galaxies that they observed. Now, the H1 deficiency is telling you how much H1 is missing in a galaxy compared to what you'd expect given its optical appearance. And it's on a log scale, so where you see 0, it means that a galaxy has a normal amount of H1. Where you see a positive number, it means that the galaxy is missing H1. And what you see here is that essentially galaxies all the way from the outskirts of the cluster to about 1 Abel radii have a fairly regular, fairly typical H1 content. Their H1 deficiency is 0. While when you move in the innermost region of the cluster, their H1 deficiency increases, and their measured H1 mass is a factor of 3 to 10 lower than what you'd expect, given the optical appearance of the galaxy. And so that was one important first hint, which I've already implied in my introduction, and that is that galaxies change morphology in dense environments because they lack cold gas, they lack a cold interstellar medium. But why is that the case? And first observational evidence of why that is the case came again from, well, this time from interferometers actually. Work done in the late 80s and early 90s started to show what the H1 distribution is like in these galaxies living inside galaxy clusters in dense environments. And what you see here is H1 shown in white contours on top of an optical image in grayscale. And you see that the H1 disk is essentially entirely confined within the stellar body. And that's not like what you typically find in galaxies living outside clusters in the field, where the H1 disk is usually a fair bit larger than the stellar body. And so these results are showing that galaxies in clusters lack H1, lack cold gas, because their H1 disk is being truncated. So they're losing a lot of their gas from the outer regions. The next important step after this lesson was to actually try and see why these H1 disks were truncated. And for this, we had to wait somewhat deeper H1 observations, done again with interferometers. This is another case of a galaxy inside the nearby Virgo cluster, observed with the VLA. And what you see when you go to higher sensitivity is that next to the inner part of the H1 distribution, which is again also in this case confined within the stellar body, you also have gas at lower column densities that is actually being removed from the stellar disk, is basically being pulled out of the stellar disk. What we think is happening in this particular case is that as the galaxy moves within the Virgo cluster, the cold interstellar medium of the galaxy, the H1, interacts hydrodynamically with the hot intra-cluster medium, which is a dense hot gas emitting in the X-rays. And this hydrodynamical interaction causes a run pressure, which effectively pulls the interstellar medium out of the stellar disk. And that's what you see in these regions here. And so this is a beautiful demonstration of why these H1 disks are actually getting truncated. The final step after these studies is, of course, taking larger samples, observing larger samples, and seeing what the H1 distribution is like over tens or hundreds of galaxies. And this is the image you see now on the right is showing the sum up, really the final result of a big H1 surveys done with the VLA. It's called VIVA, done by Eric Chang and collaborators, where they observed a few dozen galaxies, spiral galaxies in the Virgo cluster. And you see them, in this case, superimposed on an X-ray image of Virgo itself. You see a wide range of H1 images, H1 disks of varying size and shape with varying level of disturbances, indicating, without going too much in details in this case, many different evolutionary paths for H1-rich galaxies inside the Virgo cluster. All right, so this is what we knew up to, say, 10 years ago or so about the Virgo cluster, but in general, most of what we know about galaxy evolution and the removal of H1 from galaxies in dense environments, which is really the way these galaxies will then get their morphology transformed. Much of what we knew came from the study of a fairly limited number of massive clusters. Virgo is one of them. Other more distant and more massive clusters were also important targets like Coma. But we're still quite far from reaching a complete view of how all these processes of transformation of galaxies work across the entire cosmic web. And the cosmic web, the large-scale structure of the universe is very complex. It's not just made of big clusters and everything else. It's made of large voids, sheets of matter, filaments, groups, and clusters of varying mass and size and concentration, of varying dynamical status, because many of these are still growing, merging with one another, are creating smaller substructure as they keep growing. The cosmic web is a very dynamic structure which keeps evolving all the way until now, redshift 0. And therefore, to really fully understand how galaxies evolve in all different kind of environments, we need to go beyond the current view of just a few massive clusters. And if you want to make progress, there are probably two highly complementary and I think equally important ways. One is to observe large chunks of the cosmic web, like the one that you see on this slide, and try to really observe galaxies in all kinds of different environments and look at, in particular with focus on their H1, look at their H1 mass and morphology and kinematics. But an equally important, I think, complementary approach is to actually focus on a specific region of the cosmic web that haven't been studied very much so far and from which we can learn a lot. And that is the approach we've taken with the MeerKAT Fornax survey. So let me focus on the Fornax cluster indeed for the rest of the talk. I should say at the start, if you have any question during the talk, please feel free to interrupt at any time, I don't mind. All right, so why Fornax? Why is Fornax important and why are we studying it in detail? First of all, Fornax is important because it's very nearby. Its distance is just 20 megaparsec from us. It's just slightly farther away than Virgo, which is 15 megaparsec. And so you can really study how galaxies evolve in a cluster in great details. At the distance of Fornax, 1 arcsecond is just about 100 parsecs. And that is, of course, why it's interesting to study individual systems like a single cluster. When you go back to what I was mentioning earlier, how about studying large chunks of the cosmic web to get statistics? It's a great approach, and it's good that it is being pursued with ASKA pathfinders, but necessarily by going wide area, you will need to compromise on sensitivity and resolution. And that is something you don't need to do for such a nearby target as Fornax. We can study it in great details. The other important part of Fornax is that it's a small cluster. Its virial mass is just 5 times 10 to the 13 solar masses. The radius, the virial radius is 700 kiloparsecs. So it's really, you can see it as a very large galaxy group or as a very small galaxy cluster. It's somewhere in between, and it's representative of a type of systems that are not particularly well studied, in particular in H1. And so the question is, how does galaxy evolution proceed in an environment of this kind? If you look at an image of Fornax, like the one here, you immediately see that it's dominated by early type galaxies. So most of, or many of its galaxies have lost their interstellar medium. They're now evolving passively. So it's clearly an environment that has been able to shape the properties of galaxies, but how? Through which processes? I've already alluded to the interaction, the hydrodynamical interaction between galaxies, ISM, the interstellar medium, and the intracluster medium of galaxies. Is that, for example, something important in an environment like Fornax? Fornax, of course, does have an intracluster medium, but because it's a small cluster, this intracluster medium has a lower density than in the inner regions of more massive clusters. Another important aspect of small clusters is that the velocity, the typical velocity with which galaxies move within them is low. It's lower than in bigger clusters where the dispersion is higher. And so you've got, at the same time, you've got a galaxy population, a population of galaxies that move slower within an intracluster medium which has lower density compared to bigger clusters. And because hydrodynamical interactions typically scale with the density of the intracluster medium times the velocity squared of galaxies through the intracluster medium, if you go through the numbers, you'll see that, for example, drum pressure is about 10 times weaker in Fornax than in a cluster like Virgo. So hydrodynamical effects should be weaker. At the same time, because galaxies move slower relative to one another, and they're also quite densely packed close together in Fornax, the efficiency of tidal interactions when they pass by one another is quite high. It's much higher than in a cluster where galaxies move very fast relative to one another and the encounters last very little time. And so, in other words, in a cluster like Fornax, we expect a very different balance between hydrodynamical and tidal interactions than in a more massive cluster. And so within, having said this, really the main questions, the order 0 questions that we're interested in are, firstly, can we find direct evidence of galaxy transformation in a small cluster like Fornax, knowing that such evidence exists in more massive clusters? And if so, what are the physical processes that are driving this transformation? And that's why we're interested in studying Fornax in detail. All right, before we started our MeerKAT survey, we actually looked at Fornax with a different telescope while we were waiting for MeerKAT to come online. We observed Fornax with the Australia Telescope Compact Array, and this is the subject of the PhD thesis by Alessandro Loni, who's just actually defended his thesis at the local university in Cagliari. I won't go into the details of this because I like to focus mostly on the MeerKAT results, but I'll just go through a few basic results we obtained with ATCA just to set the scene for what's next. What you see here on the left-hand side is a sky view of the Fornax cluster. The gray circles are individual cluster members. The blue circles are galaxies we detected in H1 with ATCA, down to an H1 mass sensitivity of 10 to the 7 solar masses, roughly. And the green outline is the footprint of this ATCA survey, while the large gray circle is the virial radius of the cluster. So you see immediately here that the H1 detections in Fornax tend to avoid the cluster center, just as we saw earlier in Virgo. You see a similar result also on the right-hand side plot, where I'm showing a projected phase space diagram, where now the galaxies, both the normal, so say the H1 poor cluster members, the gray circles, and the H1 rich cluster members, the blue circles, are shown on a plane where I'm plotting along the x-axis the radius, so the distance of galaxies from the cluster center normalized to the virial radius, and on the y-axis the velocity of galaxies relative to the cluster systemic velocity, normalized in this case to the velocity dispersion of the galaxy population. And so what you see here is, again, galaxies tend to be at large radius, but when they are close to the center, they tend to be at high velocity. So they avoid this inner region of the phase space diagram, which is the region where most galaxies are virialized. And that means these galaxies are essentially all first infolders. They're galaxies that have only recently joined the cluster. Because of this, they are an interesting population to study, because they are recent infolders. We can study in this object whether the Fornax environment is having any immediate impact on these galaxies that are coming in for the first time. We looked into that with for Alessandro's thesis in different ways. This is just one of them, where we looked at the scaling relation, at how these galaxies compare to typical H1 and star formation rate scaling relations. So what you see here is, on the left-hand side, H1 mass plotted against stellar mass for the Fornax H1 detections in blue, and for a control sample of field galaxies in gray. And on the right-hand side, you see a similar comparison between Fornax H1 detections and a field sample, a non-cluster sample, on a plane of star formation rate versus stellar mass. What you see on these plots is that these first infolders in Fornax are, if anything, just moderately H1 deficient. They're not very strongly H1 deficient, as you would see in more massive clusters. And also they are only moderately, their star formation rate is only moderately weaker, below what you'd expect for a field sample. And I won't go into too many details of this now. I'm happy to take questions on this later, but this is essentially an indication of cluster galaxies in Fornax are evolving at a fairly slow rate. In more massive clusters, what can happen is that as soon as galaxies fall in, their H1 is removed very quickly. So they drop quite far down in this plot. And the star formation rate doesn't realize yet, because it's got still plenty of molecular gas to keep star formation going for a little bit. And so it remains in line with the expectations for field samples. So in massive clusters, you can have, in the presence of very rapid removal of H1, a population of galaxies with little H1, but relatively normal star formation. And this is not what we're seeing in Fornax, which is, we argue, and again, I'm happy to elaborate on that later, an indication of that evolution in Fornax is fairly slow. Time scales comparable to the depletion time of gas through star formation. And of course, the other thing we could start doing with ATCA was to look at the H1 morphology, so how actually H1 is distributed in these objects. Here you see an H1 contour on top of an optical image. The H1 contour is in red. We saw a few cases of probably offsets between the H1 and the stellar body. The most interesting case maybe was this galaxy here, which I'll get back to later, where you already see, even in this very small picture, an H1 tail pointing away from the cluster center, which is this galaxy here. And so that probably is a galaxy that is losing some of its H1 in the Fornax environment. But these ATCA data were quite limited because the angular resolution was just about 1.5 arc-minute. And in order to really study the physics of galaxy evolution in detail in this environment, what we need to do is to go to much higher resolution and possibly also sensitivity. Which, of course, brings me to the MeerKAT survey. Now, the MeerKAT Fornax survey consists of a survey of both the cluster central region, you see it here. This red cross that I'm pointing to is NGC 1399, the biggest early type galaxy in the cluster, at the cluster center. So we're covering the central region. The magenta circle here is the virial radius again. But we're also stretching all the way to another massive galaxy, NGC 1316. That is the host of the well-known radio galaxy Fornax A. And that is also the central galaxy of a group which is falling into the Fornax cluster for the first time. So we want to cover essentially both the cluster center and also this infall region towards the southwest. And we're doing so with 91 individual MeerKAT pointings. For each of those, we integrate about 10 hours. And eventually, because of the large overlap between these pointings, we get an effective integration time of roughly 25 hours of MeerKAT time. And that gives us fantastic sensitivity. Up to now, the current status is that we've actually observed a bit more than 50% we've taken a bit more than 50% of the data. We're going full sensitivity and building up the mosaic at full sensitivity as we proceed. We've done so far 2 observing campaigns. Fornax is up at night around, well, let's say between September and January, thereabout. So we've just completed the second observing campaign. But between the first and the second one, we've assembled about 50% of our data. And the blue line here is the footprint of the data of the MeerKAT Fornax survey as it is at the moment. And in the next few years, we will complete the rest. So we've taken about 500 hours of data so far. I will actually focus in this talk on the results that come from the first observing season, which we carried out between October 2020 and January last year. We already have, in fact, H1 images also for the 50% survey mark that I was telling you about earlier. But let's say that we've had a chance to carefully consider and look at the results mostly for the first year of data. As I mentioned in the introduction, actually, on the way to this survey, we spent quite a bit of time commissioning the telescope, helping with the commissioning. And so I want to also quickly walk you through some of the results we obtained with that. Commissioning was done mostly observing this very interesting field centered on Fornax A, this infalling group that is falling now into the cluster center. And we obtained a number of interesting results in there. Just very quickly, the first one was published by myself in 2019, was an H1 study of NGC 1316 itself, the host of Fornax A. This is a well-known merger remnant. The interesting bit and the kind of mysterious bit about this galaxy is that it is a well-known merger remnant. You see a very disturbed optical image in grayscale here, full of streams and loops and shells in stellar light. And because of its molecular gas and dust properties, it was thought to be the result of a major merger between a large lenticular galaxy and a 10 times smaller Milky Way-like spiral galaxy that brought in this dust and molecular gas. The mystery was that this galaxy should have brought also a lot of H1 with it, and this H1 was nowhere to be found until we observed the galaxy with MeerKAT indeed while commissioning, because there we found these two long tails of H1. What you see here are just a collection of H1 clouds with these arcs, which I drew by hand. But if you look at the H1, not only in 2D, but also at the 3D distribution of H1, so looking also at the kinematics, you see immediately that these are very coherent distributions of gas. And these are two tidal tails that essentially were hiding, and that is where the missing H1 was hiding. So with this observation, we basically confirmed and closed this story and solved this mystery of the missing H1 in this merger remnant. With even deeper H1 observations of the same system, which you now see rotated, here north is up, east is west, east to the left. What we found in a paper by Dane Kleiner, published last year, was a complex distribution of H1, but also H-alpha, so ionized gas, inside the medium in between galaxies in this group. You see here NGC 1316 itself, a few companion galaxies to the top left and the top right, and these filaments and clouds of H1 in blue and H-alpha in magenta, distributed across throughout this entire group of galaxies. And the puzzling thing here is how this H1 can actually survive in this hostile environment, which I'll get back to in a moment. But it's really a reminder of how complex the flow of cold gas and the thermal state of gas can be in between, inside, but also in between galaxies in these environments. Filippo Maccagni studied this object also in radio continuum, again using MeerKAT commissioning data, and he published two papers on this in 2020 and in 2021. This is a beautiful Fornax A image that came out of this MeerKAT data. You see the two giant radial lobes, but also what we were able to do, thanks to the great UV coverage of MeerKAT, is to resolve at the same time not only this fluffy diffuse radio continuum emission, but also at higher resolution the S-shaped jet in its inner regions. What Filippo did was to study the spectral energy distribution of these radial lobes, the red and blue lines here, as well as the jet, this is the magenta one, and the kiloparsec radio core of this galaxy, going all the way from MWA frequencies with at hundreds of megahertz, all the way to Planck frequencies at hundreds of gigahertz. And here you see also the MeerKAT data somewhere in this region. And through careful modeling of this, it was able to quantify the timescales of the flickering of the nuclear activity of this source, where the radial lobes have last been injected of relativistic particles several tens of million years ago. More recently, the S-shaped jets have formed, and while judging from this flat spectral energy distribution, the kiloparsec size core of the galaxy is still now active. So there is a rapid flickering of the AGN activity on timescales of essentially tens of million years. And that is probably partly explained by the presence of so much cold gas in the environment around this galaxy, which can rain down onto the AGN and fuel its activity. And last but not least, just last week, I believe, we put a new paper on arXiv, still based on this commissioning data, where we combine the MeerKAT data with ASKAP data. The ASKAP data are the image you see here in the background. It's a polarized emission of Fornax A. And what we found is that one of the H1 tidal tails I was showing earlier, which is this tail here, is coincident with patches of depolarized emission in the Fornax lobe. And basically, we made a careful analysis, which I encourage you to go and have a look at in this paper by Francesca Loi, where she was able to estimate the magnetic field associated with this H1 tidal tail. To the best of our knowledge, it's the first time that the magnetic field has been measured inside an H1 tidal tail. So this tidal tail is made of material that was removed from a spiral galaxy involved in the merger and carried with it hot gas, ionized gas, the magnetic field, which is possibly shielding the cold gas in this tail from the environment around it and allowing it to survive for a long time. All right, so this was all just from one particular observation that we took while commissioning. But of course, we are now dealing with the real survey data. And so let me go back to this first year of observations where we focused on this stripe going from the center of the cluster toward the southeast. We made a number of H1 mosaics. This is just to show you the beauty of this data. That's the H1 column density sensitivity in atoms per centimeter squared as a function of resolution. The red line is what we expected to get. The blue line is what we measured from our mosaic cubes. And in fact, we've got more mosaics at 10 arcsecond, 30 arcsecond resolution, and so on. And they're all beautifully on spec. And with this data, we went from this picture of the cluster, which is what I showed earlier to you from ATCA, to this picture of the cluster with MeerKAT. And so the immediate thing that jumps to the eye is the presence of lots of H1 clouds and H1 tails in the cluster, which we had not been able to detect and see with the previous data set based on ATCA. And that's all thanks to primarily the great sensitivity of MeerKAT, but also its fantastic UV coverage, which allows us to observe H1 emission on a range of scales, so go very deep on a range of scales, which means we can catch H1 emission, and in particular these tails and streams and clouds on any scale in which they are present. The data themselves give us a sensitivity in H1 mass down to roughly 10 to the 6 solar masses, while in column density we go down to 10 to the 18 atoms per square centimeter at the resolution similar to the one of the ATCA data, which was about 1 arc-minute, but also very competitive column density sensitivity at higher resolution. And when you look at these tails, the way they're distributed in the cluster, immediately there is something that jumps to the eye, which is that they're all, or most of them, are oriented radially with respect to the cluster center. You see here the cluster center is this green circle here, and with a number of spokes that you can see trace quite nicely the elongation of some of these H1 tails, most of these H1 tails. And when that happens, typically, this is an indication, because this is a population of first infallers, most likely in radial orbits. This is an indication that the tails may be, at least in part, tracing the hydrodynamical interaction between the H1 in galaxies and the intracluster medium, which may come as a bit of a surprise because of what I said earlier, that these hydrodynamical interactions are probably not very strong in Fornax. But the origin of the tails is quite mysterious, and I'd like to spend the last 5–10 minutes of this talk going into a bit of details on one of these galaxies to explain and to make you appreciate how complex this can be and how careful the analysis should be in order to gain some insight. And so I'll focus on this galaxy, which is NGC 1427A. This was historically the best candidate for unpressure stripping in the Fornax cluster. You see on the left-hand side the optical image of the galaxy observed with HST. And there is this front of H alpha emission towards the southeast, which had for several years been interpreted by many authors as an indication of a compressed interstellar medium because of ram pressure. And this compression is causing then an enhancement of star formation along this edge of the galaxy. In this case, so you'd have a ram pressure wind hitting the galaxy from the southeast. In this case, you'd expect an H1 tail going towards northeast, sorry, from southwest towards northeast. And already with our ATCA data, we saw that this was not the case because we detected a tail going actually in the perpendicular direction. So already we realized that things were not as simple, and this was not an obvious case of ram pressure stripping. The tail was just going inconsistent with this idea. And then when we saw the MeerKAT data, we've been really blown away with the details of this H1 distribution. That's what we see in H1 with MeerKAT. Here I'm showing different contours for the different resolutions at which we can actually image H1 with MeerKAT. The black contour is at a column density of 10 to the 18 atoms per square centimeter at a resolution of about 1 arc-minute. And then you step up in angular resolution and column density according, as you can see in the legend. With MeerKAT, when you compare the two tails, we are finding that the H1 tail is 3 times longer and 50% more massive than what we could see in the ATCA data. But really, the great thing is that we can study the tail in a lot more detail, both the kinematics and the morphology. What you see here is a position velocity diagram on the right-hand side of the H1 along the axis that you see in green on the left figure. So here you see in grayscale the H1 image. The red contours are just contours from an optical image. So you see the main part of the stellar body. And this axis cuts through the H1 tail. And you see on the right-hand side the velocity along that axis. So here, the bright part here is the H1 in the main stellar body of the galaxy. And you see this beautiful H1 gradient that we see now for the first time because we can combine great H1 velocity resolution and angular resolution. This is a gradient that we couldn't map with the ATCA data. And what you see here is that there is a clear velocity gradient with H1 becoming increasingly more blue shifted. You should see that the velocity is actually in meter per second here is decreasing as you move up. So the H1 is becoming more blue shifted as you move away from the stellar body along the tail. So there is a blue shifting component there is some interaction, some force that is blue shifting this H1 as it goes away from the stellar body. And this is completely consistent with the hypothesis of ram pressure, because the galaxy is strongly redshifted relative to the intracluster medium. So relative to the intracluster medium, the galaxy is moving away from us. And so a tail, as the gas in the tail moves away from the stellar body, it gets progressively more and more blue shifted relative to the galaxy itself. That's what we're seeing here. So that'll be consistent with a blue shifting component of ram pressure. And this is another beautiful result we can only now start getting with MeerKAT because of its resolution. That's the H1 velocity field in NGC 1427A. And what I'd like you to focus on is this green region of the velocity field. That is the line of H1 that has the systemic velocity of the galaxy. And it has this very peculiar, within the stellar body, so forget about this bottom part, within the stellar body, it has this very peculiar U shape, which is not what you'd expect in a rotating H1 disk. In a rotating H1 disk, you'd expect to have something like this, either a straight line, or in case of a slight warp, which is quite clear in this data, an S-shaped isovelocity contour at systemic velocity. In this case, you've got a U shape, which you can reproduce, and this is just a toy model, not necessarily a fit, but you can go from this to this U shape that we observe if you add a blue shifting component to the gas in the outskirts of the galaxy, and an increasing blue shift as you move away in radius. And so not only we're finding that H1 in the tail is subject to a blue shifting component, probably around pressure, but also H1 in the outer parts of the galaxy is being blue shifted. And these are the parts where the gravitational potential of the galaxy is weaker. And so again, a blue shifting run pressure has an easier time displacing the gas and giving it this extra kick. And so I'm really getting to the end. What we're finding with 1427A is that H1 kinematics, both in the disk of the galaxy and in the tail, are consisting with a blue shifting run pressure along the line of sight, which is entirely consistent with the fact that the galaxy is redshifted relative to the cluster, to the intracluster medium by 500 kilometers per second, which is a lot. The tail itself is oriented on the sky it goes towards southeast. So we think there is also a southeast bound component of the run pressure. This component points away from the cluster center, so that would support the fact that the galaxy is moving radially. However, an interesting point here is that this component of run pressure on the plane of the sky must be fairly weak. And we know this because if you look, if run pressure is pushing gas towards southeast, so it's hitting the galaxy from northwest going southeast, and if it were strong enough, it should also compress the H1 in this northwestern region. That's, after all, for example, what you see in the classic run pressure strip galaxies in Virgo. You see in the case on the right, the gas is being pushed towards the top right, and the opposite side, the bottom left side, you see a strong compression of the H1. That's really not what we see here. So that is to say the run pressure component on the plane of the sky is fairly weak. But if it's weak, how could it create this very long H1 tail pointing southeast? And so what we are finding in this case is that most likely the run pressure was not strong enough to create the tail in the first place, but it was strong enough to shape its properties, its kinematics, once the tail had been created by something else. And that something else obviously is a tidal interaction in this case. The galaxy is, after all, quite a train wreck. And you might remember the optical image of the galaxy here. And so what we are concluding in this work, and it's a paper we are trying to wrap up in the coming weeks, is that essentially the galaxy is itself a merger remnant. Thanks to the merger, some of the gas is being pulled to large radius by tidal forces, and once it was there, it was far enough from the gravitational binding of the galaxy and could be further displaced by run pressure, creating these velocity gradients and this U shape of the kinematical minor axis and so on that I've described. All right, so I'll conclude here. This last part I realized was maybe a bit more complex, but I really also wanted to give you the idea that once if you want to really gain significant insight into what the kind of processes that are shaping these galaxies in a cluster like Fornax, you really have to get these very detailed, very high resolution and sensitive observations. And when you do that, the picture unavoidably becomes complex, and you need to be ready to spend quite some time scratching your head and making sense of the data, which I think we're getting to. So let me conclude by just saying that after 50% of the MeerKAT Fornax survey, we have demonstrated, I think, that even a small cluster like this one hosts ubiquitous H1 tails and clouds that reveal for the first time in Fornax the ongoing transformation of H1-rich galaxies that are at the first infall into this cluster. I've taken as an example in GC 1427A to say to give a result which I think applies to many of these H1 tails, having had a look at many of them, and that is that these tails are probably not purely caused by run pressure, but are the result of a first tidal and then hydrodynamical interaction, where the hydrodynamical interactions are fairly weak, but are sufficiently strong to remove and displace from galaxies gas that had already been perturbed by a tidal interaction between galaxies or between galaxies and the overall cluster potential. And I hope a lot more interesting insight will come in the coming months and years. So thank you for your attention.
Thank you very much, Paolo. Thanks for sharing your work. That's very insightful, and we look forward to seeing what we can learn from the rest of the data to be released. Yeah, questions? You have a question, you can paste the question in the chat, or you can just unmute and then ask Paolo directly. I see a hand from Dominic. Dominic, yeah. Please.
Yeah, thank you. You showed us very impressive data, very enjoyable. I wonder how, since you reached 10 to the 6 solar masses in H1, do you detect dwarf galaxies in the Fornax cluster there? And do you see some gradients for the H1 content compared to the stellar mass in them too?
Yes, we do detect a number of H1 galaxies, so of dwarfs, I'm sorry. Several of these little clouds you see here are actually dwarf galaxies.
Okay. And
there are some here. There are lots actually around the GC 1365, which really has quite a number of H1 dwarfs around it. The incliner is the first author of the paper where I showed earlier on the H1 and H alpha filament near Fornax A, is now actually working on that actively and is trying to characterize the H1 properties of these dwarfs. In terms of systematic variations with if I understood correctly your question of the H1 content relative to the stellar mass as a function of position in the cluster, I think we're a bit short of statistics yet. Hopefully we'll get more of that when the survey goes on. And this statement holds true for this first year of data. Right now we already have twice as many data, and maybe it will become more interesting. But one interesting thing that I think I saw in these preliminary results by Dane is that most of these H1 detected dwarfs, if you look at their H1 content and compare it to typical H1 content of dwarfs in the field, they are kind of in line with field properties. So there are hundreds of dwarfs in Fornax, and we only detect a few of them, but those that we detect have a normal H1 content. Those that we don't detect, because we go very deep, are really, orders of magnitude below what the H1 mass you'd expect if they were in the field. And so this, I think, and we're discussing this with Dane actively, I think this probably points toward very fast H1 removal mechanism. If a dwarf has H1, for whatever reason, maybe it's just fallen in, it's got just as much H1 as it has as if it were in the field, but if it doesn't have H1, it's really got like 10, 100 times less than it should have. So it goes very fast, which kind of makes sense, right?
Yeah. There may be a few more, if I may just add on to that discussion.
Yes,
one interesting point is really if the surface brightness of these objects play a role. So you have objects which have lost their gas or during evolution before the infall into the Fornax cluster, and or if they are really having this gas loss during the infall. I think maybe looking at the surface brightness of, or the central surface brightness of these galaxies on the morphology may help on that, because that could be another thing. If you have groups which are already pre-processed, then you will have the same effect and not the strong, the high speed or the short time where you make this transition. Because I would expect that the transition would be slower here from the same arguments which you presented, that you have a lower RAM pressure effect in the cluster compared to MeerKAT, for example.
Yeah, I agree with you. I agree. It's an interesting suggestion. Yeah, we do have the surface brightness, of course, of the stellar body of all these dwarfs through the work by Renier Pelletier and his group with Fornax Deep Survey, and it's definitely something we should look into. Yeah.
Okay.
Thank you very much. Is there any other questions from anyone? And also write your questions in the chat and I'll read it out for you. I think that'll be all. I think the talk was very clear, Paolo. Thank you very much for your time and for sharing your work with us. I look forward to seeing your paper you are releasing next week or so, whenever it is. But yeah, thanks to everyone for your time.
Okay, thanks for having me.
Sure, thank you very much.